In the last class, we have seen how to derive the voltage distribution in a string of suspension type insulators, right? So we got that V3, which is the voltage across the insulator disc, which is nearer to power conductor, and V1 is nothing but the voltage across the disc, which is nearer to cross arm, and V2 is the voltage in between these two. So these are the voltages which we have derived, and these voltages are also expressed in terms of any one voltage, right? And we have seen that the voltage distribution is not equal. Why it happens? The voltage distribution is not equal due to the shunt capacitance, especially, or this shunt capacitance is also called as mutual capacitance. Because of this shunt capacitance or mutual capacitance, the current gets divided, so that the voltage across each and every insulator disc is not same. Okay, that is the reason why the string efficiency will be lesser, right? What is the string efficiency? We have seen that the let me write the formula for string efficiency. So string efficiency is equal to uh, operating voltage or total voltage across the string, total voltage across the string divided with number of insulators multiplied with voltage across the disc, voltage across the disc. Disc means insulator disc, okay, across the disc nearer to power conductor. This is the string efficiency formula. If you want the string efficiency in percentage, you need to multiply this ratio with 100. Now, for a three disc insulator string, as we have seen in our previous class, that the total voltage is the summation of all these three voltages, V1 plus V2 plus V3, right? So, mm right. Now, let me write that formula. So, V1 plus V2 plus V3 divided with N. What is N? N is 3 multiplied with the voltage across the disc nearer to power conductor. It is V3. Now it is V1 I have written as it is. I can write V2 as V1 into 1 plus K, as we have derived in the previous class or previous session. V2 is V1 into 1 plus K. Similarly, if I want to express V3 in terms of V1, I can write it as V3 is equal to V1 into K square plus 3K plus 1. So V3, in place of V3, what I can write now? V1 is into K square plus 3K plus 1. Total divided with 3 times V3. V3 means again V1 into K square plus 3K plus 1. Is it right? Multiplied with 100. This is string efficiency. In both the numerator and denominator, you have V1 as common in each and every term. So I can cancel this V1, V1, V1 and V1 here. If you take V1 as common, you'll get 1. So 1 plus K plus K square plus 3K plus 1, total divided with 3K square plus 9K plus 3 multiplied with 100, and it is equal to you have 1K square term, so plus K square, and 3K plus K, which is 4K plus 1 plus 1 plus 1 3. So K square plus 4K plus 3 divided with 3K square plus 9K plus 3 multiplied with 100. This is the expression for string efficiency in terms of the ratio between mutual capacitance and self capacitance. Okay, so what is mutual capacitance? Between the metallic link and supporting tower, you have a capacitance, and that capacitance is mutual capacitance or shunt capacitance. This is C dash, and this is self capacitance. The ratio of C dash to C is K. Now I have expressed the string efficiency in terms of only k. How can I reduce the string, or how can I make this string efficiency as 100%? So it is possible only when, so string efficiency will be 100%, will be 100% if k value is equal to 0. If k is equal to 0, this term is 0 and this term is 0, you have only 3 in the numerator. Similarly, if k is equal to 0, this term will become 0 and this term will become 0. You have again 3 in the denominator. So 3 by 3 is 1. 1 into 100 is 100%. Right? So the string efficiency will be 100% when and only when k is equal to 0. Now what is k actually? K actually is the ratio of c dash to c. Okay. Now we will see the different ways of reducing k value, because k is equal to 0 is impossible. Okay, practically impossible. But ideally you can have k is equal to 0, but practically it is impossible. Why? If you want to make k as 0, either c dash must be 0 or c must be infinite. C dash is 0 is impossible. Why? Because C dash is nothing but the capacitor between this metallic link and supporting tower. So it is expressed as epsilon A by D, right? When it becomes 0, when this distance becomes infinite, then only the capacitance will become 0. So this is the distance, it cannot be infinite. Hence c dash 0 is not possible, it is impossible. And also c to be infinite is also impossible. Practically you cannot get infinite capacitance. So practically the ratio of shunt capacitance to the self capacitance, we cannot make it as 0. As we cannot make it as 0, the string efficiency cannot be 100%. We can increase to a maximum value but cannot get 100%. Okay, now we will see what are the different ways of improving the string efficiency. Now it is also called as equalizing the voltage across each disk. Is it right or not? When the voltage across each disk is equal, then this summation will become 3 times V3, and this is also 3 times V3. You will get 100% string efficiency. Okay, now let us see the methods to improve string efficiency. Methods to improve string efficiency. It is also nothing but methods to improve string efficiency, and it is also nothing but or methods to equalize the potentials, methods to equalize the potential across the disks, across the insulator disks. Okay, so the first method which we follow in order to improve the string efficiency, improving the string efficiency, not 100% but improving the string efficiency, right? So first method which we will follow, which is the practically used method, which is most commonly used method. Okay, so method 1 is to increase the length of the cross arm. Method 1 is increasing the length of cross arm, okay. So we cannot increase to whatever extent we require, because there are some economical reasons, and there are also some technical issues that we may encounter when we increase the cross arm length to whatever value we require. We cannot increase it to a larger value, but we cannot increase it to a comfortable value. Okay, now increasing the length of cross arm makes k value reduced, right? So it is also called as, this method is also termed as reducing K value. Either reducing K value or increasing the length of the cross arm, both are same. Now what happens when you increase the length of the cross arm? See here, this is the supporting tower and this is the cross arm. Now you have the capacitance here. This is the self capacitance. We don't bother about this. But between this metallic link and this supporting tower, you have one more capacitance. What is this capacitance? It is shunt capacitance, C dash, and it is C. C dash is nothing but epsilon A by D. Epsilon is nothing but the permittivity of air medium between this metallic link and this metallic support. You have an air medium which is the dielectric material. So this is the permittivity of that dielectric material, and this is area. So we don't bother about this, we cannot change them also, but we can change this, right? So if D value increases, what is meant by D? This is nothing but D, which is the distance between the metallic link and metallic support, right? When you increase this D value, what happens? This C dash value reduces. When C dash value reduces, what is K? K is C dash to C, C dash over C. When C dash reduces, automatically K reduces. Okay, so by increasing the length of the cross arm, so this is the cross arm, we know this already. This is the cross arm. When we increase the length of the cross arm, the distance between the metallic link and the metallic support can also be increased. When we increase that distance, the shunt capacitance will be reduced. When the shunt capacitance reduced, the ratio between the shunt capacitance to the self capacitance also reduces. When K reduces, what happens to string efficiency? The string efficiency will be increased. In this way, we can make the equality not exactly equal. It is not possible to get exactly equal, but in this way, uh, uh, by increasing the distance between the metallic link and metallic support, we can at least bring the voltage across each and every disk to be almost same, so that the string efficiency will be nearer to 100%. Okay? So this is the first method, which is the most commonly practically used method. By using this method, we can reduce the K value to 0.1. We can reduce the K value to 0.1. Now let us see the second method. Second method is usage of guard ring. Usage of guard ring, or this method is also called as static shielding. Static shielding. Okay. So from the power conductor, which is at the lowest extremity of suspension type insulator, will provide one more guard or one more metallic plate or metallic sheet in order to neutralize the capacitance. Which capacitance? In order to neutralize the shunt capacitance. Okay, so this method is used intentionally to neutralize the current flowing through shunt capacitance, or to neutralize the effect of shunt capacitance. Because if there is no shunt capacitance, then the voltage will be distributed uniformly across each and every disk. Whereas because of this shunt capacitance, as the current is getting diverted through the shunt capacitance, we are getting unequal voltage distribution. In order to neutralize the effect of this shunt capacitance, we are using a guard ring. Okay, so let us see how it can be done. First of all, let me draw again a suspension type insulator with three discs. Okay, I am taking an example in order to understand how we can apply the method of static shielding. So this is the supporting tower. or metallic support like this, and you have a cross arm here. You have a cross arm. I am considering three disc insulator string. So you have a capacitor here, and you have one more capacitor here, and you have one more capacitor here, and this is the power conductor, right? Now, what is this capacitance? It is a C. As all the discs are of same shape, same size, and same size means same thickness here. So as all the insulators are practically of same size, same thickness, and the same material, they will have the same capacitance C C C. Now, here you will have one shunt capacitance. Here you will have another shunt capacitance, right? So this is actually C dash, and this is actually C dash. In addition to this power conductor, or we will take an extra God ring as a power from power conductor like this. Okay, so this is the God ring. Now, between power conductor, or between the metallic link and metallic support, you have a capacitance, and between the God ring, as it is also a metal, or metallic conductor, and this is another metallic link, between these two also you have some more capacitance. So let us assume, I am assuming this capacitance as Y, and this capacitance as X. Okay, now let us see how this God ring will neutralize the effect of this shunt capacitance C dash, right? Now let us see that. So this is the voltage I3. I am using the same currents, and this is the current. This is the current I3, and this is the current I2, and this is the current I1. Similarly, you also have the currents. So if here you need to understand one thing. So what is that? So that one thing is the currents will be from metallic link to the metallic support. It will be like this, and these currents are again from conductor to metallic link. So it will come like this, right? So this current, as I already assumed, this as I2, and I have assumed this current as I1. Now what about these currents? I am assuming these currents, let me see a separate color. So these currents are okay, these currents are I Y, and this current is I X, right? Now let us assume this node as the node B. Let me give a separate color. So this node is the node B, and this node is the node A. Now actually if we don't do any compensating method, if we don't allow any method, you will have different voltages across each and every disk. What are those voltages? This is V1, V2, V3. Now I am assuming with God ring, assuming with God ring, all the voltages are equal. All the voltages are made equal. With God ring, all the voltages are made equal. When you make all the voltages are as equal, V1 will be equal to V2 will be equal to V3 will be equal to V. Right? Now, what is the what is the voltage across this first capacitor X? What is the voltage across the first one? Uh, voltage across the first link capacitor. First link capacitor. We can easily find the voltage across this because one end of this capacitor is connected here and another end is connected here, and it is the same as this end, so the voltage becomes V. Similarly for this it becomes 2V. But here, first link capacitor, what is the first link capacitor? I am just giving a name for that first link capacitor, which is X. Now what is it? It is so one end of the capacitor is connected here and another end is connected here, so it is V and it is another V, totally 2V. 2 times V. 2 times V can also be written as 3 minus 1 into V. Is it right or not? 3 minus 1 times V. What is 3? 3 is nothing but the number of insulator discs in this string. What is 3? It is the number of insulator discs. Now N is nothing but 3. N is nothing but 3. So I can write here voltage across the first link capacitor, which is X here for this purpose. For the purpose, don't confuse this C with don't mix up this C with anything. Okay, so let me write it separately. This is a C and this is a C and this is a C. Okay, now what is this voltage? This voltage is N minus 1 times V. It is a generalized expression. Similarly, voltage across the second link capacitor. Second link capacitor. What is the second link capacitor here? It is Y. So Y is equal to, for this capacitor, one end is connected here, another end is connected here. So what that another end is again connected to here. So the voltage across this capacitance is V. Hence the voltage across this capacitance is also V. I can write this as V. V can also be written as 3 minus 2 into V. 3 minus 2 into V. Now in place of 3 minus 2, what I can write? N minus 2 times V. What is V? V is the equal voltage across each and every disk. Like that, similarly, we can write the voltage across Lth link. Okay, which can be you can give the name for that capacitor as L. Don't bother about that, and it is equal to N minus L into V. Because here if you observe, voltage across the first link capacitor is N minus 1 into V. Voltage across the second link capacitor is N minus 2 into V. Similarly, for Lth link, you will get the voltage across the Lth link as N minus L into V. N minus L into V. Now, when these voltages are equal, see, practically by using a God ring, at a node B, if you apply KCL at a node B, what is the incoming current from this capacitor? It is capital I2. What is another incoming current? Small ix. So capital I2 plus small ix is equal to, what are the outgoing currents? Capital I1 and small I1. So capital I1 plus small I1. This is the currents. This is the relationship between different currents at node B. Now, when I1 is equal to I2, then only you will have the same voltage across each capacitance. Okay, so for to make V1 is equal to V2. Here I have taken this, right? My intention or my requirement or my desire is to make the voltage across each disk as same. That's why I have assumed this. So in order to make V1 is equal to V2, I1 must be equal to I2. Okay, let me write it in the form of a sentence so that you can understand in a better way. To make V1 is equal to V2, we must make we must make I1 is equal to I2. From this equation, when it will happen? When I1 will become equal to I2? When small I1 is equal to Ix. Okay, and it is possible, when I1 is equal to Ix. So I am just creating one more current which is opposite to that current and of equal magnitude of that current, so that these two currents will get cancelled out. You will have the same current through this insulator disc as well as through this insulator disc, by which you can get equal voltage, right? This is the thing which we are doing by using a God ring, right? Similarly, at node A, practically at node A, what is the relationship between different currents? At node A, what is the incoming current? Capital I3. What is another incoming current? Small iy. So capital I3 plus small iy is equal to, what are the outgoing currents? Capital I2 and small I2. So capital I2 and small I2. Now again, to make these two voltages as same, I want to make the voltage across the second insulator disc and the voltage across the first insulator disc, which is third insulator disc, which is V2 is equal to V3. This is my assumption earlier at the starting of our analysis. So we to make V2 is equal to V3, what we need to do? We must make capital I3 is equal to capital I2. So capital I3 is equal to capital I2. From this equation, when capital I3 will become equal to capital I2? When Iy is equal to I2. Okay, and it is possible when small iy is equal to small I2. So these are the two very important conclusions that we may get uh, from this method. We need to make this current Iy is equal to I2 and also Ix is equal to I1 in order to get all the three voltages as same. These two conditions must be satisfied. I1 is equal to Ix and Iy is equal to I2. Now, now, uh, okay. Now, what is Ix? Ix is the current flowing through this capacitance. How can I find this capacitance? So this capacitance can be, this current is nothing but the voltage across this capacitance multiplied with this with the admittance of this capacitance, right? We know that Ix is equal to actually, what is the voltage across capacitor X? We have seen that it has 3 minus 1 into V, 3 minus 1 into V, or it is n minus 1 into V multiplied with omega into X, omega into X. And also, what is I1? I1 is equal to, uh, okay, V, is it right or not? V omega C dash, V omega C dash. So when you equate these two, n minus 1 into V omega x is equal to V omega c dash. So V omega gets cancelled. Now it implies that x is equal to c dash by n minus 1. This is the capacitance that we need to maintain in the first link. Okay, so this is the capacitor value in first link. Capacitor value in first link. Now let me write here itself. Here itself I am writing. What is the second condition? Second condition is Iy is equal to I2. So Iy is equal to I2 means, what is Iy? Iy is nothing but the product of voltage across the capacitor Y and the admittance of the capacitor Y. What is the voltage across the capacitor Y? It is n minus 2 into V. So n minus 2 into, let me write here first Iy value. Iy is equal to n minus 2 into V multiplied with what is the admittance of capacitor? It is omega into capacitance value. So omega into Y. I have not written J because J will in the LHS side and in the RHS side J will get cancelled. We just discussing about the magnitudes of the currents, right? And what is I2? I2 is equal to the voltage across this capacitance is 2 times V, because one end of the capacitor is connected here, another end is connected here. So the voltage across this capacitance is 2 times V. So 2 times V multiplied with what is the admittance of this capacitance? It is omega into C dash. Now by equating these two, you will get n minus 2 into V multiplied with omega Y is equal to 2 times V multiplied with omega C dash. V omega gets cancelled. Now Y is equal to 2 times C dash by n minus 2. This is the capacitor value. What is this? This is the capacitor value in second link. This is the capacitor value in second link. Similarly, how can you get the capacitor value in Lth link? Let us consider that capacitance as L by seeing these two expressions. Here I can write this as 1 into C dash by n minus 1, and this is 2 into C dash by n minus 2. Like that we can write L into C dash by n minus L. Okay, let us give a separate name for this so that you will not get confused. Let us give it as CL. The capacitor of Lth link is L into C dash by n minus L. How we got this? Because we already got n minus L into V, and you will get L into C dash. This expression is very important. CL is equal to L into C dash by n minus L. CL is equal to L into C dash by n minus L. What is L? L is nothing but the number of link to which we need to find capacitance. To which we need to find capacitor. We need to find its capacitance. And C dash is nothing but the shunt capacitor value, and N is nothing but the number of insulator discs in the suspension string. In this way, by maintaining different capacitances, see here, C dash by n minus 1 is one value, 2 C dash by n minus 2 is another value. Is it right or not? And L C dash by n minus L is another value. Like that you are getting different capacitances. In order to get the different capacitances, you need to change the distance between this metallic link and God ring as we move from power conductor towards crossarm. When we are moving in this direction, we need to change the distance between them. Why? Because we need to get different capacitances. X value is different from Y value is different from Cl. As these capacitances are of different value, you need to increase or decrease the distance between the metallic link and the god ring when we are moving from power conductor to cross arm. Okay, that is the reason why I have drawn it in the form of a curve, not exactly with a straight line. When you keep it as a straight line, you have the same distance between them. When you have the same distance between them, you have the same capacitance here and here, but you must have different capacitances. That is the reason why I have drawn it in the form of a curve, right? So this is the way of applying god ring, sorry, way of connecting the god ring, and by using this god ring we can neutralize the effect of shunt capacitance. See what we are doing here, we are making these two currents as equal, I1 and Ix, and we are making these two currents as equal. By making these two currents as equal, we can neutralize the effect of this shunt capacitance, and by making these two currents as equal, we can neutralize this shunt capacitance. So with the help of God ring, we are actually neutralizing the effect of shunt capacitance, so that the currents through all the self capacitances or all the insulator discs will remain same, by which the voltage across each and every disc remains same. Okay, so the problem with this method is we need to add one more god ring, which increases the cost of transmission, and it is very difficult to follow this method, because it is not easy to connect a god ring to the power conductor for the entire length. So that is the reason why we prefer rarely this method. Okay, so this method also has one more drawback. We cannot increase the length of the cross arm to whatever value we require. There are some economical reasons and there are some technical issues that we may encounter when we increase the length like this. So there is a limit for reducing the K value. We cannot reduce it to 0, but we can reduce it to 0.1. This is about method 1 and method 3. We also have one more method, but this method is not at all using nowadays. But let us know what is this third method. Okay, so third method is grading of insulators. Third method is grading of insulators. Grading of insulators is nothing but, as we are having different voltages across each and every string, what we will do is we'll use uh, uh, various discs, various discs in the same string, in the same string of suspension type insulators. We will use various discs of different sizes, various discs of different sizes, according to the voltage distribution, according to the voltage distribution. Okay, voltage distribution. Let us see how it is done. So you have a supporting tower here, and you have a cross arm here, and you have the insulator disc. See, we have observed that when we are moving from power conductor to cross arm, the voltage across each and every disc increases, sorry, reduced. As the voltage is getting reduced, first, the for the disc which is nearer to cross arm, we will use a small disc. After that, we will increase the thickness of the disc, means we will use some more bigger disc here, and we will use some more bigger disc here, like this, and you have a cross arm. Why we are using the disc with more thickness? Because this is the disc which experiences a large amount of voltage, and this is the disc which experiences a very small amount of voltage. Hence, I want to use a small insulator, means I want to use an insulator of small thickness, and here I want to use the insulator of large thickness. In between them I want to use the insulator of this thickness, right? In this way we can use the insulator properly, we can use the insulator discs properly, but this is practically very difficult, practically very difficult. Why it is practically very difficult? Manufacturing the insulators of different sizes for the same string is obviously very difficult to do. Okay, so manufacturing or preparing, okay, so insulators manufacturing the insulators of different sizes for the same string, of different sizes of for same string is very very difficult, and it is also an expensive task. Okay, for example, logically, and it is also expensive. For example, logically, assume that we have an industry, we want to manufacture some goods, right? For example, plastic bottles. Logically, I'm explaining this with a small example. If I want to manufacture the plastic bottles or water bottles of same size, it may be not difficult, because you need the machinery of a similar type in order to manufacture the plastic water bottles of same size. Whereas if you want to manufacture the water bottles of different sizes, then you need to have the different machines, different types of machines, in order to manufacture the water bottles of smaller sizes you need a smaller machine, and for bigger sizes you need a bigger machine. So when you have when any industry have the different equipment, means when it has the equipment of different types, it is very difficult to maintain it. Okay, so that is the reason why I am saying that manufacturing the insulators of different sizes for same string is very very difficult, and it is also expensive, and it is also expensive. That is the reason why it was used in olden days but not used nowadays, the grading of the insulators. So these are the three different methods of improving the string efficiency, or methods to utilize the disks properly, or methods to equalize the potential across the disks. Okay,